The Hopfield network makes for an interesting study for a number of reasons. Firstly, as discussed in previous videos, its publication was one of the spurs which caused a resurgence of interest in neural nets in the early 1980s. Secondly, its operation illustrates for us why recurrent networks are considered to have memories. And finally, it will show us something of the intrinsic operation of recurrent nets and their stability. In fact, the Hopfield network in its pure form isn't particularly useful, but it makes an excellent tool for explaining these issues. Hopfield was actually not particularly interested in trying to illustrate AI principles with his network, but was interested instead in physical particle spins in substances called spin glasses. Let's start by considering the topology of a Hopfield net and its operation and its neurons. The network is a single layer, and as shown on the screen, it has the same number of inputs, outputs, and neurons. So if there's 3 inputs, there's also 3 outputs, and 3 neurons in the single layer. There are 3 feedback paths present, which are labelled FB1 to FB3 in the diagram. You can see perhaps that a good way to describe a network is symmetrical. The neurons act like simple threshold units, but with outputs of +1 and -1. So a 0 output is -1 and a 1 output or an on state is +1. To run a pattern through the network, it is first applied to the inputs and the outputs are calculated as normal. Next, the pattern is removed from the inputs and the output values which we have just calculated are fed back to the inputs via the feedback paths FB1, FB2 and FB3 in the diagram. These now provide new inputs and the output can again be recalculated from these. This process is repeated again and again until the outputs stop changing and settle down to stable single values. During this process, as the network settles, it is said to relax. If the networks keep changing and never relax, then the network is unstable. Hopfield showed mathematically that if 2 conditions are met, then the network will always be stable. To understand these conditions, however, let's first label the weights. The weights are labelled with 2 numbers. The first number is the input the connection is coming from, and the second number is the neuron that the connection is going to. Thus, W23 is a weight going from input 2 to neuron 3. You can see this in the diagram on the screen. Hopfield showed that the network is stable providing that Wn, m is equal to m, n and Wn, n is equal to 0. This means, for example, that W1, 2 should be equal to W2, 1 and W1, 1 and W2, 2 should be equal to 0. The training algorithm which Hopfield derived and which we will discuss in the next video automatically satisfies these constraints, and this automatically provides a stable network.